Hi, I'm Jiacheng, and today I'd like to talk something about our paper, Updatable Learn Index with Precise Positions. Recently, as we all know, machine learning has been widely developed and also has been successfully in many different application domains. As a database researchers, we're easy to find there are two popular trends of research in DB area. The second one is just the DB for machine learning. This is not the main part of today's talk. And the first one is machine learning for database systems. So the sense is that to replace core components of database systems with machine learning techniques to achieve better performance and use less space. Just as plotted in the figure, we could replace traditional indexes, query optimizers, scheduler, and etc. with machine learning ones. This paper, as mentioned in title, just focus on the indexes. Indexes play an essential role for both TP and AP workload in DB systems. Traditional indexes just ignore the features of data. For instance, in the extreme cases, suppose the keys are just contiguous integers, and then we only need to minus the values of first key and obtain the position of the current keys. Thus, simply maintaining the offsetting indexes is enough. The above observations brought to learn indexes. In its paper, all indexes can be simply considered as models that map keys to their corresponding positions. Besides, they allow arrows around the predict positions. For B tree, the arrow is just the page size since we need to search inside the page. As for learn indexes, it just guarantees the arrow bound on the constructions and use binary search around the predict positions to find the real ones. However, those learn indexes also have some problems, such as limited support for dynamic operation and also incur too much cost for both lookups and insertions. The left figure is the structures of learn indexes, and it is just a recursive model. The topmost ones will use linear regression to decide which models in the next layer the input keys belongs to. Finally, in the love models, they just predict the positions where keys ought to locate. We also need to use binary search to find the real positions around the predict positions. The above can be done correctly since keys are stored contiguously. The advantages of learned indexes compared with traditional ones is that it saves some search cost in non-leaf nodes and also reduces the tree height due to the large nodes. Learned index is hard to support insertion, and here comes Alex. In this index, keys are stored separately and nodes use gapped array structure to further support insertions. Alex also mentioned the model-based insertions, that is, tries their best to insert elements around the predict positions. It will also trigger unbounded element shifting and need exponential search around the predict positions. Besides, Alex has a structure modifications which will split large nodes. We also mentioned PGM in our paper, but due to time limitation, we skipped to talk about it. Thus, analyzing the problems of previous indexes, we find those dynamic mechanisms are all flawed. Lookups require binary or exponential search around the predict positions, and each insertions will also lead to element shifting or subtree structure merging. So, we proposed our index loop. The core idea is to avoid inaccurate predictions. That is, all predictions made by our models are exact. Then we could eliminate significant and inevitable overheads. But here comes two major problems. First, we need to avoid conflicts. Conflicts happen when predictions for different keys coincide at one position. We also need to restrict height to bound indexes complexity, even in worst cases. Thus, we should think new structures and would utilize an adjustment approach to balance the tree. This is a structures of loop. Each node contains a kernelized linear model, which is A multiplied gx plus b. Here, G is a given kernel function and should be monotonically increasing. Besides, node should contain entry array and a bit vector to indicate the entry types. Each entry has three types. Now means the entry is an unused slot, and the data entry stored key and the corresponding values or pointers. Finally, node entry stores a point to the node in the next layer, thus forming the index tree. Next, we just show a sketch of lookup and insert operations. Recall that our idea is the precise positions. However, it seems implausible since learned models are hard to be perfectly exact. Thus, we just require elements should be inserted in their predicted positions. And we will create new small nodes to hold the conflicting elements if new insertions cause conflicts. Therefore, lookups are so easy that only need to traverse along the index without additional binary or exponential search. Moreover, insertion do not need to shift elements to create a gap. However, simply applying the above procedures may cause tree unbalanced and heavily leaned. So we need adjustments to reshape the tree. There are two questions about adjustment. First, when a node should be adjusted, we propose two criterions. Only when there are too much insertions or conflicts happen in a node and its corresponding subtree, does the node will trigger adjustment. Besides, we suppress adjustments on nodes with too many or few keys. As for how to adjust, we summarize the following 5 steps. We first collect and sort keys in the node and its subtree, then build the optimal model. Based on the model, we dispatch keys to different positions or entries. We then create nodes for those conflict positions and apply the above procedure recursively. So the remaining question is how to obtain the optimal model. We will define the conflict degree, which captures a maximum number of conflicts at any position in the entry array. The better the model is, the lower the conflict degree it has. We ought to find a model to achieve as low conflict degree as possible, that is, from given keys and entry array lengths to obtain model parameters. After some calculations, we have the conditions for both A and B, which is depend on T. In order to make A and B visibles, we thus obtain the restrictions of conflict degree T. From the equations and the right figures, we find there are some repeated calculations and verifications, and then we devise a greedy algorithm to find a better T and therefore also for A and B in linear time. And thus, each adjustment can also be done in linear arithmetic time. Also, we analyze the several approaches and propose the complexities in the worst cases. The cost of lookup operation is at most logarithmic time, and the amortized cost for insert operation is at most polylogarithmic time. As for evolution, we used 4 datasets from Alex's paper and compared with Alex, PGM, Learning Index, B+ tree, ART, and BW tree. We also prepared 4 types of workloads: read-only, read-heavy, write-heavy, write-only. For read-only workloads, our index achieves up to about 3 and more times throughput than other state-of-the-art indexes. For read-write workloads, we could see the similar trends. More other detailed evolutions can be found in our paper. In conclusion, we just try to address the bottlenecks of the previous learned index structures by forcing precise positions in loop. Moreover, there are also future possible works like how to make index adapt to different types of keys and how to support concurrency controls, or etc. We also show the links of our paper and the code if someone would like to refer them to acquire more details. So, thanks for your time.